Hey guys, Mr. Betts here. We are going to continue adding to our toolbox of derivative shortcuts. So far, we've looked at shortcuts for different types of functions like polynomials and sine and cosine and exponential functions, natural log functions. And so the product rule is going to allow us to take derivatives of functions that combine those. So we're going to use the product rule now, and then in that next topic, we're going to do the quotient rule, and it's going to allow us to use those derivative rules in more of a variety of types of functions. So essentially with the product rule, what's going to happen is we're going to have a function. In this case, the function we want to take the derivative of is a of x, and a of x is defined as the product of two different functions. So we might say f of x is like sine of x and g of x is x squared. Those are both functions that we know how to take the derivative of individually, but if we have a function that is sine of x times x squared, now the product rule is going to allow us to do that. So if the function is the product of two functions, then the derivative is going to be given by this equation right here. So essentially, it's the derivative of the first function times the second function plus the first function times the derivative of the second function. So notice that f prime of x and g prime of x here are the derivatives, and I'll give you in a minute some ways to help remember that, but this is just a rule that we want to memorize because we're going to see lots of functions that are products. Before I get into that, though, I want to talk about why it works. So this is kind of getting into the nitty-gritty with the limit definition. If I want to find a prime of x, that's going to be using the limit definition. The limit is h approaches 0 of a of x plus h minus a of x all over h. And so for this particular function as a product, that's going to be the same thing as the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. Now, to accomplish this, I'm going to do a little trick here of adding and subtracting the same thing in the numerator. So by adding and subtracting the same thing, I'm not changing the value, but I'm going to throw some terms in here that will allow us to rearrange and get what we're looking for here. So what I'm going to add and subtract is going to be something that that will allow us to factor with this factor here and this factor here. So I'm going to add, I'm going to subtract first. So I'm going to have f of x plus h. So my first term is going to stay the same, times g of x plus h. But then I'm going to subtract f of x times g of x plus h. Then I'm going to add that. So I'm going to add f of x times g of x plus h. So by subtracting and adding the same thing, I'm not changing the value of it. And then we have minus f of x times g of x. And all of that is over h. And just in the interest of time, I'm going to do this. So I'm going to split this up into two fractions. All of this over h. Okay, so since the whole thing is over h, I can put each individual one over h. Now, you might notice that in the first one, we have a g of x plus h in both terms, and in the second one, we have an f of x in both terms. So I'm going to factor those out. So we have the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x all over h. And then we have plus the limit. And I'm going to write this as two separate limits. Remember, the sum rule for limits says that when we're adding two terms, we can split it up into two separate limits. So I'm going to split it up into another one, factor out that f of x. And hopefully you are noticing something that should look a little bit familiar. So in the first one here, we have the g of x plus h. So as h is approaching 0, when h gets really small, this g of x plus h is just approaching g of x. So we're going to have g of x there. And then the limit as h approaches 0 of this, that's the limit definition of the derivative for f of x. So that's going to be f prime of x. And then in our second limit, this f of x here doesn't depend on h at all, so that's not going to change. So we have plus f of x. And then this right here is the limit definition of g of x, the derivative of g of x. So as h approaches 0, that is going to be the derivative of g. And there's your product rule. So a prime of x is equal to, now I have these switched from the way I had it written on the first slide there, but the derivative of a is given by the derivative of f times g plus f times the derivative of g. So by doing this, by showing that the product rule works, now we can take the derivative of functions that are more complicated, and complicated by multiplying one type of function times another type of function, and we can take the derivative of that using this rule. One more thing I want to just point out here is a lot of what I've talked about is multiple representations for problems. So we might see the product rule written in different ways. So this top one here, this is how it was on that first slide. But we might see that as just the derivative of f times g as this right here. So it's the same thing, but we don't have all those f of x and a of x and all that stuff. We might do a problem like this using substitution and substitute u and v and make those represent the functions. Typically substitution problems in calculus and other math will use u and v to represent other things. We might have a function that's defined y equals u times v, and using what's called Leibniz notation with those differentials dy dx, we can say the product rule that way. Just verbally, we can think of the product rule as derivative of the first times the second plus the first times the derivative of the second. Honestly, when I'm doing a product rule problem in my head, this right here is what I'm thinking as I'm working through the problem. So all of these are just different representations of the same product rule. And when we start seeing problems that are represented different ways, knowing that these are all really equivalent is going to be helpful to us.